Now, we're happy to welcome our next speaker, Dr. Darren McKnight. Dr. Darren McKnight is currently a senior technical fellow for LeoLabs. Darren leads efforts to realize the value proposition for the growing global network of ground-based radars for space situational awareness, space safety, and the space sustainability. He creates new data depictions, develops risk algorithms, and leads space incident investigations. He's focusing on creating new statistical collision risk assessment approaches to provide valuable context to the operational collision avoidance support provided by LeoLabs worldwide. The presentation title is "The Mean is Meaningless." Over to you, Dr. McKnight.
Great, thank you so much, Ping. I appreciate the opportunity to speak today. All right, so there's a lot of people are talking a lot about orbital debris. I got my PhD in the area in 1986. I was the first person to get a PhD in the area and wrote the first book on it. So I know a lot of people have a lot of opinions. As I like to say, opinions don't matter when facts are available. So what I want to do today is just give you some facts, right? That's very exciting working for LeoLab, as we have a global network of radars looking up and acquiring data. I came to work for them just because I needed more data. So when I say the mean is meaningless, people like to have generalities like the fragments are going to kill us, the constellations are big, they're going to be horrible. What I'm going to tell you is, if somebody tells you something for sure, they're for sure wrong, all right? And so the generalizations that I think are true is that we need to understand the components of orbital debris. So I'm going to tell you in low Earth orbit, it's the same thing, by the way, in MEO and GEO also, but we primarily look at low Earth orbit. You can kind of think about everything up there being in clouds, clusters, and constellations. So there's clouds of fragments. Over 200 things have blown up in space. I'm so sorry. It happens all the time. It's really unfortunate. But 50% of all of the trackable fragments have come from just 6 events. So again, it happens a lot, but only 6 of these things have really caused the majority of the risk from the fragments. Clusters of massive objects. So unfortunately, orbital debris includes both the fragments and dead hardware. So abandoned rocket bodies, non-operational payloads. And the interesting thing about this, when you look at the risk on orbit, I usually say the number of objects tells you the current risk. The mass of objects tells you the future risk, because those big objects colliding with each other are going to be what's going to be the long-term evolution of that lethal debris. As the previous speaker broke, as Aaron mentioned, the lethal non-trackable debris, what you cannot see can kill you, unfortunately, in orbit. But 30% of all the mass is only in 5% of the objects, and specifically in rocket bodies that are in very tight altitude bands. So I'll show you those also. And the last thing is constellations. Somebody has some questions about space traffic management. That's what we do. We provide space safety services for about 70% of all payloads in low Earth orbit right now, to provide conjunction data messages for them to do collision avoidance. And the question before was, did everybody have collision avoidance capability? The fact is, unfortunately, no. Believe it or not, there still is not a requirement. And as these constellations grow in size and in number, that's going to be very, very important. So as we go through this talk, brief talk today, I'm going to go through it fairly quickly because I love the questions and answers at the end much more than lecturing. I used to be a physics professor, and I'd much rather get to the end and have a dialogue with all of y'all. So just think about clouds, clusters, and constellations. So this is a map that we call about the neighborhood. So I'm often called the new space realtor. Location, location, location. Where you are matters. So a real quick look in this diagram is, if it's dark blue, then that means it's operational payloads. If it's light green, that means it's dead rocket bodies. If it's light blue, that means it's non-operational payloads. And if it's orange, it's fragments. So just having that color, what you can see from the overall population is about half operational payloads, about half fragments. If you look at these 100-kilometer bins, as I call the neighborhoods in low Earth orbit, you can see they're drastically different. down in human space flight, almost everything is an operational payload, whether it be the space station or hundreds of CubeSats. There's not a lot of debris for a lot of reasons. Mainly atmospheric drag pulls them out. As you move up in altitude, you see how the characteristics change drastically. More and more fragments, fewer and fewer operational payloads until you get to OneWeb. Now, all of a sudden, not a lot of fragments, but a lot of operational payloads. So when I say the mean is meaningless, it shows you the neighborhoods in low Earth orbit vary drastically. And that means that what we should be doing to manage that risk is also going to be very different at in those different neighborhoods. So let's look at the breakup cloud. So this just is a very busy slide, but this I could brief on this for an hour alone, but this just sort of shows the distribution of all the fragments from breakup events in low Earth orbit. And so what I did is I just sort of said, give me the top 6 breakup events, and what the top 6 breakup events give you are about 50% of the numbers I mentioned. And this shows you where the debris is distributed as a function of altitude, largely where the events occur, but also where atmospheric drag doesn't have a major effect. So the debris from these events are going to last a long time. They're going to linger for a long time. So what are those 6 events? Well, I just showed them listed here. The good news and the bad news is 2 from China, 2 from Russia, and 2 from America. So people like to say it's all China's fault or all America's fault or all Russia's fault. Guess what? When it comes to fragment clouds and mess that we've made, of the 6 top break events, we're equally responsible in making a mess. So you saw a chart earlier that Aaron showed about showing the spatial density of objects. This is now a spatial density. I know you can't read the scale on the left side, but it's just a log scale of the number of objects per cubic kilometer. You all can see the big spike here for Starlink. And so you might go, oh, that must be really dangerous. Not necessarily, right? Because a constellation, there may be a lot of satellites in a small region, but they can manage their risk. It's kind of like the Indy 500. They're 6 inches apart going 200 miles an hour, and it's not that unsafe. Whereas on the highway near me here in Northern Virginia, 6 inches away, that's near death, right? So you got to have a couple car lengths. So in these, just the spatial density alone isn't really critical. I draw the 25-year orbital lifetime because that's really, really important. The orbital lifetime of objects left in low Earth orbit are driven largely by atmospheric drag, which is driven largely by altitude and solar activity. So around 615 kilometers, an intact object will linger for up to 25 years. If it's above it, it's going to stay around longer. If it's below it, it's going to come down sooner. That's a really important number because that's what's been sort of the standard threshold that we need to live by, is don't let objects linger for more than 25 years. Unfortunately, we've been woefully inadequate in meeting that objective, and we're woefully inadequate in saying we should reduce that to a 5-year rule or a 1-year rule. So the 25-year lifetime is really important where that is. So this is the spatial density with the number of objects per cubic kilometer. And this now is a plot that shows you the mass per altitude. Again, don't worry about the actual units on the left side, just get a physical feel. And what you see is on the left, the numbers, the Starlink and some constellations down low, and then a big stack of debris, big stack of fragments, right? Over here, now you see a completely different look. You still have a spike for Starlink, but as I said before, they manage their own risk very, very, very well. As a matter of fact, the 5,000 Starlink satellites has less risk than 100 uncontrolled satellites in any other orbit, right? So again, the numbers don't always mean anything, but you see some spikes here, 775, 850, 1,000 kilometers. We'll talk about that a little bit later, but already you can see that, oh, it's bad here, no, it's bad here. Depending on what you're measuring, it's a different story. So this is an interesting story. What I actually do at LeoLabs is I take all the events that occur in space and in low Earth orbit and look at the conjunctions of those and add up the probability of collision times the mass involved. Probability times mass involved is a surrogate for consequence. That gives me a risk. So what I can do is I can actually give you an aggregate risk by altitude for the probabilities times the mass involved. And what we see is there's a huge peak here around 840 kilometers. Well, why is that? Well, unfortunately, there's 18 SL-16 rocket bodies. These are Russian rocket bodies that are 9,000 kilograms. They're 11 meters long, 4 meters in diameter. They're like a big yellow school bus, but they have no brakes and they have no steering wheel. They're just going and going and going. The whole bunch of U.S. Satellites left up there. There's been a number of small U.S. breakup events, and the largest breakup event overall, which is the Chinese ASAT test, all occurred in this region. So as I like to say, it's a unfortunate, ironic collaboration in space, just as I mentioned before, for the 3 major spacefaring countries. In its specific altitude, this is the bad neighborhood. This is the neighborhood you don't want to wander into. If you want to look at other regions, you see there's some spikes here. Some Chinese rocket bodies and some dead US payloads kind of make these spikes come up. The spikes also from a bunch of Russian SL-8 rocket bodies and the payloads that they left, plus the Iridium Cosmos collision that occurred back in 2009. And then there's another peak of SL-8 rocket bodies. Those are Russian rocket bodies and the payloads they left. So what you see is, again, a different look when you're looking at actual risk of events. So these are the regions. Now, what are the objects involved? This is a way for us to map out the actual 40 worst conjunction events over the last 2.5 years. So this shows you that it's going to be involved with Chinese rocket bodies, US rocket bodies, pieces of debris from a NOAA breakup. So it's a wide variety of things. So again, when you want to blame it on somebody, you can't always, depending on which chart I show you, you can blame it on one group versus a different group. And so this just shows you where these events took place. Notice I did it 615 kilometers and above, because again, I'm worried about long-lived orbits. As Aaron mentioned earlier, the Cosmos 1408 Russian ASAT event, that was unfortunate, but a lot of it decayed very, very quickly. So if we want to go from the top 40 events to what are the families of objects that are causing the biggest problem, now what we see here is that Ping-Yang 1C debris cloud is created the greatest number of conjunctions of concern, like on the order of 15,000 events over the last 2 years, and the highest total risk. But in addition, some of these new CZ-2C Chinese rocket bodies also are in total presenting the greatest risk. So these are some of the kind of objects you want to remove. We can even go even further than that. How about specific objects? So there's a paper I wrote a few years back with 19 of my international colleagues. What are the top 50 objects that need to go? Now I can calculate that every single day by pushing a button. So on looking at this, the top events, 3 of them are fragments. Well, we're not going to go remove a fragment. Those fragments are really bad because they're near things. There are 2 Russian non-operational payloads that are involved a lot. But as we've been hinting a little bit, some of these big rocket bodies, Russian rocket bodies, Chinese rocket bodies, have been a major, major concern. So we've talked about fragments. We've talked about clusters of dead things. How about constellations? Well, constellations are on the rise. And this is a fairly modest assessment of where the number of satellites in these constellations are going to be. But we're talking about 75,000 operational satellites potentially in low Earth orbit by the year 2030. And right now we have on the order of, in constellations, about 6,000 currently. But the important thing to keep in mind, though, is the 2,000 to 6,000 other satellites right now actually pose more risk to the environment than these large constellations. So why is that? Well, the evolution of the safety margin has really changed over time. When Cosmos 2251 and Iridium 33 collided in 2019, it changed everything. It changed US government support to worldwide understanding of issuing these conjunction data messages. But there are some old-fashioned ways in which that's being done. And one of the old-fashioned ways of doing things is within these conjunction data messages, the US Space Force doing this for free for the entire world, by the way, on the US taxpayers' dollars. You know, you thank all of us taxpayers. They early on said, I'm not going to try and figure out how big each object is. I'm going to assume that every non-operational payload is a 10-meter hard body radius, so 20 meters in diameter. Every rocket body is 3 meters, and every fragment's 1 meter hard body radius. Well, at LeoLabs, we don't do that. We don't use default, we use actual, because as we get more and more crowded, we can't have that safety margin all the time, because we might be overreacting to things that we shouldn't be overreacting to. So we spend a lot of time of making sure that we give the best answer. Now, what the 18th Space Defense Squadron gives is very good, very safe, very reliable, but it might be overstating it depending on the size of the fragments. So to close out real quickly so that we have time for some discussions, constellations are getting the lion's share of attention, but quite honestly, they are not the problem. They are going to be the victims of poor understanding about leaving objects up in orbit for 10, 20, 30, 50 years after their operational lifetime. And it was okay to kind of do that 20 years ago, but now we know better. So it's really interesting on that point is, in the last 20 years, we've had more rocket body mass abandoned in low Earth orbit per year than we did the previous 45 years before that, despite the fact that for 20 years, we've been saying this is a really hard problem, really hard problem, really hard problem. We're not getting any better at it. So that's going to be that's a real big concern for me, that we haven't learned our lesson. And lastly, fragmentation events are abating slightly. The intensity and persistence have generally reduced over the last 10 years. But if you look at the overall cycle, what we see is a lot of really, really close approaches, a lot of events between these massive derelicts. And we foresee those events starting to happen in the next decade. So unfortunately, as we've cleaned up, no more ASAT testing and some other things, we're going to be replaced by collisional problems. So I wanted to make sure I ended on time. I started a little bit late and I ended right about on time. So we should have a couple minutes for question and answer. Sorry about running through that so quickly, but I'd rather talk with you than lecture to you.
Thank you very much, Dr. McKnight, for a great presentation and the enthusiasm as well. I can see some questions from the audience. Maybe we can just read that out right here. Is it possible to detect and avoid the space debris using satellites on board radar system rather than detection using radar systems on the ground? Well, it's not. Okay.
Oh, I'm sorry.
This is first question. Yeah, please go ahead.
Okay, so the fact is, potentially it can contribute to the problem, but what you really have is a field of view and a propagation error, right? So if you can see something with a space-based radar for your own system, the question is going to be, if you can see that object, is it too late? And if you're looking at sort of crossing trajectories in advance for worrying about the positional uncertainty, I'm not sure what it adds to you other than more mass on your satellite, which gives you more area, which then gives you more collision cross-section, which increases your risk. So there's been a lot of studies done on that. Basically, you're better off for the big stuff to be looking at it from the ground because you can get much better custody of it with a global network of radars. There was an idea of doing that for a space shuttle in the early days, and that was scrapped because it wasn't useful.
Yeah, thank you. And another question from the same audience is that, what are the space organizations such as NASA, etc., doing for removal of these growing space debris?
Great question. So JAXA, Japanese Space Agency, UK Space Agency, European Space Agency have really been leaning forward about committing money to removing objects on orbit, doing technology demonstrations. NASA just released last month this new space sustainability strategy, where they actually talk about removing objects, which was really, really nice to see, right? Because in the past, honestly, NASA's been sort of behind the times relative to JAXA, UKSA, European Space Agency, and even New Zealand Space Agency had all been more forward-leaning, committing money, looking at technology demonstrations. So NASA's catching up, but but really JAXA is kind of in the lead in my mind. They've been very good stewards of the space environment and space sustainability.
Great. Maybe you can have another question answered. Does the French Graves space radar provide any public international space debris or payload orbital threat data for collision avoidance use?
So you probably should talk to the Europeans about that. However, EU, the European Union has put together this SST network where they've tried to take all of those radars and optical systems and provide as a conglomerate some capabilities to provide conjunction data messages. At this point in time, I don't believe that they're providing a lot. They still use the 18th Space Defense Squadron. Many commercial companies in Europe will use LeoLabs. It's a fine radar, but a single radar doesn't do much for you when it comes to improving space safety or understanding the effects of debris mitigation rules, because you've got to be able to see things on a regular basis. So it's always a network that makes the difference, which is why we put radars all over the world, right? It's because you gotta have that global diversity. So a single radar by itself is tough. I'm sure it's a great contributor. It's a great instrument. But directly it probably does very little. But as a conglomerate, the EU SST network should be starting to provide more and better space safety information.
Yeah, if you don't mind, we can maybe have a couple more questions if we still have time to keep tracking. Yeah, another question is, what is the current protocol for collision avoidance?
Yeah, the current protocol is not to have a good protocol. So the current protocol is the most responsible operators bear the most burden. So I will tell you right now, there's a number of folks who have operational satellites that interact with Starlink, and they don't communicate at all with Starlink. Starlink, on the one hand, they put out their ephemeris, which is basically like if you're driving on the highway, that's like you telling somebody, here's my Google map where I'm going to go for the next 30 minutes. So you know exactly where they're going to turn and everything. They use their blinkers. There's a lot of smaller groups of satellites that interact with Starlink that don't do that at all. They don't share that information. They don't follow any standards. They don't call each other. Whereas like OneWeb and Starlink, they work very closely together. When OneWeb's going through that, they're calling in advance, they're sharing information, they're talking about thresholds, about at what PC level are you going to make a collision avoidance maneuver? Are you going to do it 1 day in advance, 2 days in advance, 3 days in advance? All the information being shared. So unfortunately, the protocol is the most responsible people are working with the most responsible people. As I mentioned, you can have 6,000 operational satellites and they pose less risk than 100 poorly managed spacecraft. And so I really appreciate they asking that question so I could foot stomp on that. Numbers does not mean risk. How you behave is what poses the risk.
Yeah, maybe one last simple question is, what organizations need to be involved in reducing these risks?
Yeah, so regulatory folks that that will issue licenses for launching obviously are very much involved in this, right? And so that's great to see. I think there needs to be something more global though, because unfortunately at the UN what we have is a great system that any great advance can be rejected if one country says no thank you. So you end up having this sort of everybody's happy with it means nothing real is happening, right? So I believe it's going to have to be those regulatory agencies. And again, we have the FCC in the United States, but who's going to do that in Europe? Who's going to do that in Africa? Who's going to do that in China? Who's going to do that in Japan is different. So there's any one of those organizations, regulatory, operational, right? Just having like, there's an organization called IEEE International. It's a group of all the countries who are interested in debris. But again, it's also consensus. So I think what really has to happen is I think that the US's FCC has really led the way. They're the only organization that's saying a 5-year rule, you have to bring your stuff down after 5 years after it's useful. They're the only ones in the world who have pressed for that, right? So I think that them leading the way and somehow the regulatory folks from around the world have to join together and do. So I think it's a regulatory community, because they're the ones who say, yes, you can fly, no, you can't fly. And they can even put things in place now where you said you're going to do it, you didn't do it, you have to stop launching. Oh, that's bad, right? There's actually some enforceability. Whereas some of these other organizations like the UN, they'll go, that's not good. And then they just keep doing it, right? And so I think that's the problem. So I think regulatory agencies have the potential, and FCC's really set the good example. So the bad news is, I don't think we've done great at NASA for the debris remediation or removal, but in America for the FCC, we've done a really good job of being forward-leaning in the regulatory. So if we had JAXA and the FCC, we'd be set. That's the good combo there.
Thank you very much again for the presentation and Q&A, Dr. McKnight.